So let's talk about resistivity and resistance in conductors. So as we talked about in class already, you can have an electric field in a conductor if you allow for the fact that charge can move. And if you have a conductor where you allow charge to move in a circuit, you can have the steady current without building up charge somewhere. So the steady current will flow. And you'll have a finite electric field in the conductor. Now what we will show is that the electric field and the current that flows are related through, if you assume a certain model, through something called Ohm's law, a relationship called Ohm's law. So it turns out that you can write this as the current density, which we defined in class today, is equal to the conductivity times the applied electric field in the metal. So this is what's moving the charge. Another way you can write this, just flip it over. The electric field is the resistivity. Now the book uses rho for resistivity, which is just silly. Okay, I'm going to use eta, which is the right way to do it. So E is equal to eta J. Okay, and eta is the resistivity, and that's just 1 over sigma. Okay. So let's quickly see where that comes from. So we can derive this expression if we make an assumption about the motion of electrons inside the metal. Okay, so we can write down an equation of motion for an electron in the metal. So m dv dt, that's the acceleration, is going to be due to the forces. So we have QE. Q is negative here, but we'll leave it algebraic, I guess. Okay, and then there's a force, as we talked about today in class, is a drag force. So it's not just freely accelerating in the metal. There are other electrons and other atoms around in the metal that it bumps into. So there's an effective drag force, and as we discussed in class, you reach terminal velocity. So as we'll show in a second, the electric field pushes you. You run into a bunch of atoms, and that and this drag force results in eventually will balance the electric field, and you'll get no net acceleration, and you'll just get a steady drift. Okay. Now we have to use a model for the drag force, and in reality it's very complicated, but you can use a simple model. And a simple model for a drag force is that the drag is proportional to the velocity. So one way to write that is m times nu, where nu is some collision frequency or drag coefficient, times the velocity. Okay. Now if we look inside the metal, the electrons are they have a temperature. Okay, so they're bouncing around inside. So you can cast the velocity in two terms. There's going to be a drift term due to the fact that there's an electric field, and then there's going to be some fluctuating random thermal velocity. I meant to draw a tilde over the top. There you go. So this is fluctuating thermal velocity here, and this is in response to the electric field. Now the average over time, or an ensemble average as we like to say, the thermal fluctuations on average don't go in any particular direction. And so those average away, and we're left with this drift velocity. Okay, and in that limit, so we'll argue there's a terminal velocity, that this drift velocity is the result of a balance between the electric field and the drag force. And so this, in that limit, we're going to have dv dt equal to 0. Okay, so with that, we can just equate the two forces, the drag force and the electric force. Okay, and so this leads to 0 is QE minus m nu, which is this collision or drag coefficient, v drift. Okay, or the drift speed due to collisions balancing the electric field is QE over m nu, where nu is this collision frequency. Okay, all right, so that's the drift speed that you get when you apply an electric field into a metal where there's some drag due to collisions with atoms. Now I said in class, I talked about this Plinko game on Price is Right as an example of this drag process, and so I thought I'd find a YouTube video. There we go. I got Snoop Dogg in it. That's pretty good, right? So this is like YouTube within YouTube. It's something's going to blow up if I do this, I suppose. All right, so I'm going to just show you the video. Okay, here comes the actual Plinko part. So you see the board here. I'll pause it. We got, if you can see it, there's a bunch of pegs in the board, and and it's at an angle, right? So she's gonna drop her disc down into into this, and it's gonna bounce around the pegs. And the argument, if it's the same as what we've discussed here, is you'll reach a terminal velocity. It'll kind of, on average, move at a certain rate down the board until it lands in the zero, probably. But let's see what she does. All right. I wish I had Snoop helping me with Plinko. There we go. And it kind of bounces around inside the metal. Oh my goodness, she won. That's amazing. Okay, we'll stop that. All right, let's see. Let's go back here. Okay, so that process, the Plinko process, gives rise to a drift velocity that's steady, a terminal drift velocity. Okay, so the next step I want to do is connect this back to the original Ohm's law model, and I can do that by recognizing that the current density, if only one charged species is moving, this is supposed to be V sub drift, then it's just the density, number of electrons per unit volume times their charge times the drift speed. Okay, so in that case, this becomes N density times Q squared over M nu, okay, times the electric field. And so now we have our connectivity coefficient here from our model. And so the connectivity is then NQ squared over M nu. Okay? So if we take this simple model where the drag is proportional to the velocity, we get Ohm's law out of it, and this is what the connectivity looks like. Okay? And of course we can invert that to get the resistivity. And let's do that. So the resistivity then is just going to be M nu over NQ squared. Okay, and so I show you this, I ask you not to read the section that goes through this calculation. So I'm not going to hold you accountable for this, but I wanted to show it to you to see where Ohm's law comes from. What I do want to hold you accountable for is the connection between the conductivity and the resistance and what we would call resistivity, sorry, and what we would call the resistance of an object. Okay, so we're going to talk about resistors in circuits as we move forward. And so what we're going to consider is a finite piece of metal. Okay, so let's take a piece of metal that has some length D and has some cross-sectional area A. Okay, so an expression for Ohm's law that might be more familiar to you is that the potential difference across a piece of metal like this or across a resistor is proportional to the current through the resistor multiplied by the resistance, this coefficient of resistance. So let's see if we can find that given what we've already derived here. So I'm going to say that the current in this, there's going to be an electric field, and there'll be some current in here, J. All right, I don't know why I said E1. And we know from our calculation that J is sigma times E. Okay. Now, the total current flowing through this wire, J is the current density, so it's a local quantity. The total current, I, is just the integral of J dot dA, as we talked about in class. So we count up all the electron flows across a surface that we pick and integrate it to get the total current. Now we're going to assume that the current density is uniform, and if that's true, then this is simply J times A. And we've also picked a surface so that the current flows in the same direction as the surface normal. Okay. All right, so if I multiply both sides of my equation by A, let's ignore the vectors for now. So I've had J times A is the connectivity times E times A. Okay. Now I'm going to assume that I have a uniform electric field. Okay, so if the electric field is uniform in the metal, that would have to be produced by some kind of charge plate on either end, right? That's how you get the electric field in that case. Now, in a circuit, the way the electric field gets generated is much more complicated than that because you don't have charge plates. You do have charges that make the electric field, but they tend to sit on the outside of the wire. Okay, and how they can generate a uniform electric field is a good question to ask. Okay, but we'll model it as a uniform electric field, and if that's true, what I can do is remember that the potential difference between the between the two ends of the wire is just going to be E times D. Okay, so I can rewrite all of this now. So here's the expression. I can say that J times A, which is I, is the same as sigma times A. Now I'll divide by and multiply by D, ED, okay? And this is the same as sigma A over D, okay, times the potential difference. Okay, and so I can now identify, so I've got an Ohm's law-like expression that should look familiar. It looks like I equals V delta V times something. Okay, I can turn it around and say V delta V is I times the quantity D over sigma A, and I'm going to identify this as the resistance R of this piece of metal. Okay, so it depends on an intensive property, which is the conductivity, as well as extensive properties, the size. Okay, D and A here show up. Okay, now I can also write this as I times eta D over A. Okay, now eta is the resistivity, and the resistivity, if it's higher, means it's harder to push current through. Okay, and so that makes sense here. Conductivity is higher, means it's easier to push current through. So you can use either one, whatever you like, but they both give you an expression for the resistivity. But I write down the one for eta, the resistance, sorry, of a piece. So you say the resistance of an object. The resistivity is associated with a material. It's a local, internal, intensive property. The resistivity, you have to tell me how big the object is, or sorry, the resistance. I'm screwing that up all over the place. The resistance, you have to tell me how big the object is so I can answer. And it goes like this. Okay. All right, we'll do some concept questions on this in class and check in more on it then.